So today we're going to kind of do our last lecture on gradient descent and variations thereof. And the idea is to just try and give you a little bit of intuition onto how variations of gradient descent work. We're not going to be going into like a lot of detailed proofs or that kind of thing, but it's more about getting a flavor for how these modifications work on this algorithm. Okay? So the last time, and I'm going to try to end a little early, so we'll see. So the last time we talked about stochastic gradient descent, and this is probably kind of the most important generalization of gradient descent that you need to understand. And here we talked about what do you do when you have loss functions that are of the following form. Right? So you're trying to minimize something that is f of x, but this f of x is actually the sum or the average of a bunch of other data points, right? Or a bunch of other functions. And you might, in particular, you might have m of them. And it turns out that in a lot of problems that we care about, this is actually the form that you have. And we saw, for example, that in least squares, this is the form that we have, right? For least squares, what do we have? We have, basically, if I think about our least squares is something like right? This is my standard least squares is kind of something like this, right? But if I have m rows in A, let's say A belongs to m is a constant number, does putting this 1 over m in front change my optimum point in any way? It's just a constant, right? Minimizing f of x is the same as minimizing 1/2 f of x. So it doesn't matter. So this is my least squares objective. But I can just as well write this as 1 over m right, where AI is now a row of A. Right? This is exactly equivalent to this. There's absolutely no difference. So, and here basically what you're doing is you're saying, look, I'm interpreting every single row of this A matrix, or every single row of my equation, AX equal to B, as one observation. Right? And I'm trying to put this data together and come up with the best thing from all of this data. So every one of these is my error on kind of one data point, right? AI, BI is one data, A1, B1 is one data point, A2, B2 is one data point, so on and so forth. Does everyone see this perspective? Yes? No? Good? Nodding? Somewhat nodding? Okay. Okay. So this is kind of the type of function where we want to be able to use stochastic gradient descent. And stochastic gradient descent, we said, like, well, we want to use it in cases where computing the entire gradient is kind of onerous, and we don't really want to do that. So for example, if we were computing the gradient of this function, right, then that's basically computing the gradient of each of these and adding them up together, right? It's m times the amount of work. Instead, if you could just compute the gradient of one of these, you have to do less computation, right? And so when computation is a bottleneck, doing something like SGD can save you on that kind of bottleneck. The other thing that something like SGD can do is it's basically a noisier version of the gradient, right? And when you're dealing with, for example, a non-convex problem, just doing gradient descent can get you stuck in some kind of local minima type situation, right? Gradient descent, if you started here, gradient descent, you might just end up here and have no way of getting out because the gradient here would be 0, and then you'd be stuck here forever. But if instead you kind of approximately did gradient descent but added noise, then you might bounce around to other places and you might be more likely to find something that is closer to a global minimizer. So these are some advantages of using a technique like stochastic gradient descent. Is that part clear to everyone? Yeah? Okay, good. So let's do an example, okay? So let's start with a very simple example, actually, even simpler than least squares. Let's say my f of x and I want to this is what I'm trying to do. Okay, I'm trying to minimize x. So what is this doing? Let's say I have data points p1, p2, p3, pm, okay? What is this doing? I'm saying I want to look at the distance of x from p1, x from p2, x from p3, x from p4. What is this function doing? It's doing something that we do commonly, which is? Not quite. It's averaging, right? Let's say I had 2 points. I want to take 1/2 of the distance from the first point and the second point. Like I'm basically finding an average of all of my data points, right? If p1, p2, pm are my data points, all this is doing is finding an average, right? So what is the minimizing x here? The average, right? Like it's clear to everyone that if I had 2 vectors, right? Let's just take a scalar example. If I had p1 here and p2 here, what is the point x that minimizes these two? Minimizes this function here? It's the midpoint, right? If I had 3 points, p1, p2, p3, it would be this distance, this distance, distance, like you divide by 3, right? Everyone sees that? Okay, good. So that's all that this is doing. So we know what our expected kind of answer here is. We know what the minimizer is, right? So as we talked about, stochastic gradient descent always has a decaying step size. So here let us choose eta t, so that's the step size at time t, is let's just choose it as 1/t. Okay? And I'll remind you all of what the gradient descent update is going to do. Well, I have xk plus 1 is equal to xk minus, let's say, eta k times gradient of f I at xk, right? So now there's a couple of natural questions here. We talked about stochastic gradient descent, and I said every single time, instead of taking gradient of f, right? If I didn't have this subscript I here, this would just be gradient descent. But with this subscript I now, I'm saying I'm choosing only one of these terms and taking the gradient of that. Okay? The question is, which term do I choose first? And which term do I choose second? And which term do I choose third? Right? These are all like questions that you have to answer to be able to implement this. So there's a couple of standard ways in which you can do this. One is you just set up kind of a rotation. So you take the first point first, the second point second, the third point third, and you keep going on. The second is you pick randomly. The third is you can do something that is called a mini batch, which is basically what you do is you take not just f1, like instead of just having one fi here, you have an average of a couple of fi's. You don't take all m of them, but you pick a few. Okay? So these are some common variations that you can have on this particular theme. what we're going to do here is we're going to choose i's sequentially. So we'll just choose F1 first, F2 second, F3 third, so on and so forth. Any questions up to this point? Are we clear on what we're trying to do? I just want to make sure that this, like, the procedure is clear. Yes, no questions? Thumbs up or thumbs down maybe? Or just midterm burnout? Like, midterm burnout is totally fine. So remember, here I'm thinking f of x as the sum of component functions. So remember, if I taking a gradient is a linear operator, okay? So when I write this gradient of fi, I just mean take the gradient of the function fi and evaluate it at the point xk. No different from take the gradient of f and evaluate it at the point x. Does that make sense? Okay, so we got this. So let's just say we start at x naught, let's say, equal to 0. Okay? So what is now x1 equal to? Well, x1 is equal to x0 minus 1 over 1. Let's just say here, call this eta k plus 1 so that we're not dividing by 0. And then what is the gradient I'm going to take here? I'm going to take the gradient of 1/2 x minus p1, right? What is the gradient of 1/2 x minus p1? It's just x minus p1, right? Okay, and what is this equal to? So I have x naught minus x naught. So this is equal to exactly p1. Right? Everyone following me? Okay. So now x2 is equal to x1 minus 1 over 2 x1 minus p2 is equal to p1 minus 1/2 p1 minus p2 is equal to, what's the nice thing that's coming out? So if I had 1 point, what's the average of 1 point? The point itself. What is the average of 2 points? The midpoint of them, right? So what do you hope we're going to get for x3? Is now x2 minus 1/2 x2, or 1/3 now, minus p3 is equal to p1 plus p2 divided by 2 minus 1/3 is equal to so you can see the pattern now, right? So what this is saying is that, look, I'm doing stochastic gradient descent, and I'm kind of getting exactly to the place I want to get, right? Of course, there's many things working in my favor here, right? I chose the right step size. Would this work if my step size was something different from 1 over t? I could have chosen 1 over t plus 2, right? Wouldn't quite work out. I could have chosen 1 over t squared. All of these are different ways of having a decaying step size. So I kind of rigged it a little bit to be in my favor, right? But even with all of this, like even if I had small modifications, you can see that I'd be going in the right direction. So what I want to try and illustrate with this example is that even though you're not following exactly in the direction of the gradient, you can be doing something completely reasonable, which is what SGD is doing. Okay? Everyone follow me on this example? Any questions about this? Yes?
Can you clarify what is Fi in this case?
I just clarified that. It's Fi is this term, right? This whole thing is Fi.
So if we take the gradient of it, then we can.
What is the gradient of this? It's exactly that, right? Okay, good. Questions? No, yes. The question is, why do we have to use a decaying step size for SGD, but we don't have to use one for gradient descent? The fundamental thing is that when we're doing gradient descent, right, if I have some function like this, what do I know about gradients and minimas, right? We know that if I have a minimum, the gradient must be 0 at that point, right? So if I have a minimum of f of x, I know the gradient of f of x must be 0 at that point. But do I know that the gradient of fi of x must be 0 at that point? I don't, right? So when I'm doing my stochastic gradient update, say I've reached a minimum point, right? Say xk plus 1 is my minimum, or xk is my minimum. Then I don't want my gradient descent to move me, or my stochastic gradient descent to move me. But fi of x, the gradient of fi of x might not be 0 at that point, even though gradient of f of x is 0. You see what I'm saying? And so you might, if you don't have a decaying step size, you can end up just kind of chaotically moving around, never converging anywhere. And that's why in stochastic gradient descent, you kind of force it to converge by every time taking smaller and smaller steps. So the question is, what's the guarantee, right? Like, you don't know nothing. You're just taking some random steps in some direction. What's the guarantee? And in some sense, you don't have the same level of guarantee that you have with gradient descent. When you do stochastic gradient descent convergence proofs, which are out of scope for this class, what you usually prove is the convergence of the average iterate. So you say on average, if I take a running average of my points, like let's say I take the average of the last 10 points or the last k points that I've been at, you know, xk plus 1 plus xk plus 2 plus xk plus 10. That is converging to my minimum, is the kind of proof, is the kind of results you can prove for large enough k. You cannot prove cleanly results where you will show that xk itself converges. But despite all of this, somehow this thing seems to work, right? And so that's one of the reasons, like, you know, there's so much work in understanding stochastic gradient descent, understanding variations in stochastic gradient descent. And because of the fact that you can do a lot and get pretty good results with low computational cost, everything is a trade-off, right? Like, if you could compute the exact gradient, you would. But you just can't when you have billions of data points. So you do the best you can. It's a very engineering aesthetic from that perspective. Yeah, so great question. What if the step size that you choose is really small so that it converges to the wrong place? So this is, again, like one of the big things in general in machine learning research is that how do you choose or optimize your step size, or what in machine learning is often called your learning rate. And this is what is called a hyperparameter. And you will often change it or tune it to try and understand how it behaves in different circumstances. So it could converge to a bad point if you choose a learning rate that's too small. And that would be bad. And so you often deal with this by just doing lots of trial and error on the learning rate. The other thing is that you have a lot of results and a lot of work on variations on stochastic gradient descent, where you come up with intelligent schemes to adaptively change your step size. So there's guidelines, or there's an algorithm, not just how to do your gradient update or your like evaluation point update, but also an update on the step size. So how is a dot t related to a dot t minus 1? And you know, there are various different ways that kind of adaptively choose these step sizes. There's also these ways. There's learning rate schedules. These schedules are basically strategies for the schedule by which the learning rate changes. Yeah. If I wanted to compute, the question is, what is the time and effort that you save? Well, if I wanted to compute gradient of f, right, I'm doing m times more computation than I'm doing by just computing one of the FIs, gradient of one of the FIs. I want to talk about one more example of SGD, just to give you a sense for how it works. And I want to do the kind of scalar least squares example. Okay? So the scalar least squares example is just this. If I have a1, a2, actually let me say am times x okay, so my x, my unknown, is a scalar. It's a real number. And I have m observations about it, right? a1x equal to b1, a2x equal to b2, and I want to find x. Everyone see this? This is a least squares problem? Right? Okay, good. So here, I'm going to write my f of x. Okay? So let me write it explicitly here. Fi of x is now this is f of x, this is my fi of x. Okay? So what is the minimizer? What is the x where this is? What is it? Well, first, what is the minimum value of fi of x? 0, right? X is any real number. What is the minimizer? Where? What? At what? How does fi of x equal to 0? At what x is that true? bi over ai, right? Good. And what is the gradient of fi of x? Well, that's also pretty straightforward. It's just ai times aix minus bi. Right? Okay. And what is the minimizer? Of f of x. Not fi of x, but f of x. Well, this is just a least squares problem. We know how to solve it, right? It's A transpose A inverse, A transpose B. So what is A transpose A inverse here? It's just the norm of this vector squared, right? So this is equal to 1 over and what is AI transpose B in this case? Well, matrix A is just a vector. So this is A transpose B is just seems reasonable? I'm just going to rewrite this in another way, which is I'm going to write this as So I'm connecting basically, I want to bring this bi over ai into this picture, the minimizer of fi of x. So what I want to try to observe in this setup is that there's actually some relationships between all of the quantities that are being thought of here. In particular, this minimizer of f of x, I should label it. Let's call this x star. X star, I can lower bound and upper bound by minimizers of fi of x, right? So for example, if I take sigma ai squared times max ai over, or max bi over ai, so let's look at this quantity here. X star is ai squared times bi over ai in the numerator, right? So instead of bi over ai, I say, let me replace every single bi over ai with the largest one of these ratios. Clearly, this is an upper bound, right? And then I can just pull this out, and this is just equal to Does everyone see that? So this is basically saying, look at all of your fi of x's, look at all the component functions, look at all of their minimizers, and find the largest of those. Does that make sense to everyone? Alternatively, what could I, instead of bounding it by the max, is there a similar thing I can do for a lower bound? I can do the same thing here, right? Okay? So that means basically if I was to try and draw these, right? Let's say I have, let me call this, what should I call this? X min, and let me call this X max. I have X min here, then X star is somewhere here, and then I have an X max somewhere over here, right? Basically, of the minimizers of fi, my minimizer, the one that I'm interested in, is kind of somewhere in the range of those same minimizers, right? It's in between the largest and the smallest. What do you do if an ai is, yeah, you wouldn't use that row, right? If you had an ai that was 0, you already have kind of a problem, because then you have 0 times x equal to a non-zero thing. So if you have a 0 in a column vector, that's the same thing as saying like you have a rank deficiency. That your A transpose A would not be then invertible, then you'd have all those same issues, right? So you're just going to drop that row if you had a 0 there. Let's say you're doing your stochastic jumping, you're doing your stochastic gradient descent, and somehow you pick an xk. Your xk is here, okay? It's larger than x max, okay? So what is the gradient of fi of x, whichever you choose, at point xk? Well, the gradient of phi of x we already computed. This is equal to ai times aix minus bi, which is equal to ai squared times x minus bi over ai. Right? This is the gradient. When xk is greater than x max, is this quantity positive or negative? Xk is greater than now the largest of the bi over ai's, right? So this thing is always positive, right? Greater than 0 if. So when I do this gradient step, when I move from xk here, which direction am I going to move in? I'm always going to move in this direction, right? So I'm going to always move towards where my x star actually is. So like I'm being pushed into this interval. Anytime I'm outside of this interval, my stochastic gradient descent step, no matter which I choose and no matter where I am, I'm always being pushed in the correct direction. Does everyone see this? Even though it's not exactly the gradient step, it's still moving in the right direction. Similarly, if I was over here, I'm going to be pushed. My gradient is now going to be negative, and so I'm going to be pushed again towards x star, right? I'm going to be pushed into this interval, which is my interval of interest, right? Once I'm in the interval, then it's harder to see what happens. But what stochastic gradient descent is guaranteeing me is it might not converge me exactly to x star, but it's going to converge me somewhere in the general ballpark, in the general neighborhood. We can do a little bit more analysis on this, but given the general mood in the class, I'm going to not do that. If you want, we can ask me questions about it later. I'm just going to give you 2 more little variations on gradient descent because I want you to know about these. These are things that are bound to come up in your conversations with your colleagues at your first job or your first internship or whatever kind of thing you're doing, if you're doing anything in the realm of optimization, machine learning type things. So I want you to have heard about these things. Okay? It's not 0, it's greater than 0.
Why that quantity is greater than 0?
Okay, so what is x max? X max is the largest bi over ai. It's the largest of the bi over ai. That's how we defined it. Xk is greater than the largest of the bi over ai. So is it greater than the specific bi over ai? Yes, therefore this term must be positive. This is a square, therefore it's always positive. Therefore this is greater than 0. That's least squares. Minimizer of fx, just do least squares, you'll get it. Okay, so now I want to tell you about projected gradient descent. This is kind of the other standard trick that is always used. So gradient descent, when we talked about this algorithm and when we've talked about stochastic gradient descent, we've always talked about the case where we have an unconstrained optimization problem, right? We say our optimization is over R. We never worry about whether xk plus 1 is also in our domain or not. But a lot of times, of course, you have constrained optimization problems, right? You have a limit on what kinds of points are in your domain. So for example, if you had something like this, min of f of x, such that x belongs to some set script x, right? How am I supposed to do this kind of minimization? In this case, I'm going to consider x being a convex and compact set. And I'm going to consider f of x to be an L-smooth function. can do basically what is called projected gradient descent, which is what I do is I say xk plus 1. Let's say I have this is my x, script x, and I'm here somewhere, xk. Okay? And I do my gradient descent. I do my gradient step. I compute the gradient, and it kind of takes me out here. Right? But I'm only allowed to be inside of this set x. What's kind of the natural thing to do if your gradient step, if your xk plus 1 ends up here? What would you want to do? Don't go all the way to that point, right? Just find the point inside x that's closest to where you would have wanted to go. So instead of going here, choose this point, the closest point in x to where you would have wanted to go. That's the idea. That's it. It's the obvious, natural, good idea. This is what projected gradient descent is. And so the way you write this is you write xk plus 1. Pi is often a symbol. Project onto set x, xk minus eta times the gradient of f of xk. Okay? And here, to prove convergence for this, we will choose eta equal to 1 over L. We're not going to do it. It's out of scope for this class, but the standard convergence proofs will, again, use this smoothness parameter as a step size. And if you recall, our previous proof also used 1 over L as our step size. And let me just define for you what this projection means. So if I have a point y, and I'm projecting it onto a set x, this projection is basically the argmin of x belonging to x of y minus x squared. So it's basically saying, look at every single point in x, look at the distance between y and x, and find that x such that it's closest to y as possible, as close. Find the minimizer of this, right? That's the projection. Question? Question is, what is a compact set? A compact set we haven't really defined in this class. A compact set is one that contains all of its limiting points. So that means if you take a limit of sequence, any limit point, it will be in there. So, but don't worry about that. No, we projected it at every step, because at every time step, we risk having gone outside the set, right? Sometimes, so for example, if you take a gradient step and you stay inside the step, what is going to be your projection, right? Like, okay, find the closest point from this point on the table to all points on the table. It's going to be itself, right? So the projection will be completely vacuous if you're already in the set. Okay? So this is the key idea of projected gradient descent. Any questions? A lot of the kinds of things that you can do with gradient descent, you can do with projected gradient descent. To prove convergence of this, that's what you need to choose. If you remember, our gradient descent proof also used that same exact step size. Thinking about this algorithm now, I want to ask you, is there something about this that doesn't feel very good? But here, what you're doing, you were like, oh, I wanted to minimize f of x. I had an optimization problem here, right? And now, every single time I want to do a gradient descent step, what do I have another one of? Another optimization problem. It's like we've created these nested optimization problems, right? How am I going to solve this optimization problem? Maybe I need to do another gradient descent, right? This can get bad fast, right? So basically, and this is also a constrained optimization problem. So projected gradient descent has issues, essentially, right? It can run up your computational cost high quickly because projections are expensive. And so there is a variation well, not a variation, but a different algorithm that tries to get at the same idea, or tries to do something similar, but doesn't have this projection state at every single time. Does everyone see why like this natural, simple idea that works and we can prove it works is great and is valuable in many cases, but is suboptimal at some times, right? Okay, so what I wanted, this next algorithm is called Frank-Wolf, okay? So here what we're going to try and do is we're going to try and basically do something kind of along the lines that you're thinking, which is instead of going outside and then coming back in, just from the get-go try to choose something that's on the inside. We can't do it the way you were thinking, but this is another way of trying to kind of do that, right? And so we want to move basically in the direction of the gradient of xk, right? Or the gradient of f at xk. But if we cannot move in that direction, let's say moving in that direction gets us to a bad situation, what I'm going to do is I'm going to define yk to be equal to the arg So I'm going to say, look, I want to move in the direction gradient of f of xk, right? And I want to do descent, so I want to kind of, in fact, I don't want to move in the direction of the gradient, I want to move in the direction of the opposite of the gradient. Can you find a direction y where y remains in the set, right? But you're kind of maximizing your inner product with the negative gradient, right? So it's arg min of the gradient and y. Does that make sense? Right, find that y that's inside the set, but is kind of exactly where you want it to be. So maybe a picture is a good thing to do. So like, let's say I have some convex set like this. And let's say I'm here, okay? And let's say my gradient, let's say this is my negative gradient direction, okay? So this is the direction that I want to move in, right? That's everyone with me here? I'm here. If this is my negative gradient, this is the direction I want to move in. Okay. So maybe if I choose the right size step size, I could still stay inside the set, right? But if I choose the wrong size step size, maybe I'll end up outside the set, and that could be a bad thing. And I won't know if I'm inside the set or outside the set before I take the step. I'll have to take the step and then find that out. So instead, what if I could look through all of the points here and find a direction y that is almost in this direction, but kind of make sure that I stay inside the set, right? In particular, one concrete option would be to choose kind of extend this and go all the way to the boundary, right? That would be the most aligned vector. That would be one possible minimizer for this. Everyone see that? Yes? But here, if you notice, I'm not restricting this y to be a unit vector. Y is allowed to be any length thing. So I might want to choose some other y, something like this over here. And I might choose this y here. Because this vector is longer, even though the angle is slightly compromised, this inner product still might be the best one. Okay? Do you see that? And so what I'm going to do is I'm going to choose this y, and then I'm going to take a step in the direction of this y. So what I get is xk plus 1 is equal to 1 minus gamma k times xk plus gamma k times yk. So if this is my yk. And yk is the minimizer of this particular. This minimization, because it's just a dot product, is an easier minimization to do than that projection. So I find this y, and then I say, look, I'm going to average these 2 points. So gamma k determines how much I go towards yk. Right? If I choose gamma k equal to 1, I'm basically jumping all the way to yk. If I choose gamma k equal to 0, I'm not moving at all. I'm just staying exactly at xk. Right? So gamma k is kind of playing the role of my step size. Do you see that? And gamma k is a function that, like, it's like something you define like your learning rate. It's also something that you choose as a decaying function. So over time, you're putting more and more weight on where you are and less weight on the new point that you find. And so this would take you somewhere to kind of some point in between here, right? So you're moving, you know, in a way, and because now you have a convex set, you know that this point is always going to remain in your set, right? Because you're making sure that gamma k and 1 minus gamma k are less than 1. Which you don't necessarily have there when you take any arbitrary gradient step. Why is yk on the boundary of the set? Great question. Here I drew yk on the boundary of the set because what I'm trying to do is I want to make this, so if I have an argmin of this, it's basically the argmax of the negative of this, right? And so I'm trying to maximize this inner product. So I could take, if yk was here, that would only become, like, you could only do better in this minimization by choosing a longer yk, right? So you're going to always go to the boundary point and then kind of pull back. This is the negative gradient here. I'm minimizing. I don't have a negative sign here. In this picture, I have a negative sign. So if I have a vector that's pointing in this direction, right, the most aligned vector is here. The worst aligned vector is exactly diametrically across. Is this still facing the problem of solving a nested optimization problem? Not quite as much, because finding this argmin is just a search in directions. And so this is an easier optimization problem to solve. So that's it. That's all I really want to cover. I can say more about stochastic gradient descent and Frank-Wolf and projected gradient descent, but I want to try and end a little early today. Just a quick summary of the lecture that I want you to take home from this is, first thing is that all of these are yet also just baby steps in terms of perturbations on gradient descent, right? What you want to do is basically see this as gradient descent is just the beginning. And you will learn different ways of kind of modifying the step size, modifying how to deal with the different kinds of constraints if you were to take more advanced classes. This is kind of the extent to which we'll do a little bit more of algorithms, but if you're more interested in this, definitely take a class like 220C, where a lot of this will be talked about in more detail. So that's it for today.